In this lecture, we're going to introduce differential equations, which is the first topic that we'll cover in 5371 this semester. So we're going to start very basic with first order differential equations. So first, a couple of definitions. An ordinary differential equation, or ODE, as many mathematicians will refer to it, is an equation that contains one or several derivatives of an unknown function. And usually this unknown function is called y of x. In electrical engineering, it's often called y of t because it's not uncommon for our independent variable in electrical engineering, since we deal with signals and time domain functions, to be t as opposed to x. But in many mathematical textbooks, you'll find the independent variable referred to as x. So x and t are typically your independent variables. An ODE is said to be of order n if it contains the nth derivative of the unknown function y, and if that's the highest derivative of y in the equation. So if you have a third order derivative of y, and that's the highest derivative in your differential equation, then that's a third order differential equation, and n is equal to 3. So in first order differential equations, there are two forms. I've written two examples here. Now, in the textbook, as in most mathematics textbooks, derivatives are written as primes. So when you see this variable y prime, that would be the first derivative. The second derivative would be y double prime, and so on. So the first form is referred to as implicit form, and in that case, in a first order differential equation, you would have a function of x, y, and y prime, all written such that you have an equation equal to 0. So in the second line here, you see just a simple example. What's different about this, the entire equation is equal to 0. Notice that the y prime has a coefficient x to the minus 3, so it's not by itself like we would be used to seeing it in some cases. This is a dash, not a negative sign. It's just a part of the PowerPoint format. Explicit form, you're actually expressing that first derivative as a function of x and y. So in this line is the same equation as above, just written where we've isolated y prime and set it equal to a function of x and y. So explicit and implicit forms, two different forms of the differential equation. The one you use depends on the methodology you're employing to solve the equation, what kind of equation you have, and several other things, but you will see both throughout the course of the unit on differential equations. Now, in general, differential equations will have a solution, and that solution typically applies in some open interval. This interval can be the entire set of real numbers, so it can run from negative infinity to infinity, and often does, especially in the practical functions that we'll work with throughout most of the semester. So basically, we have some function h of x, and h of x is a solution to a given differential equation if the following two situations are met. First of all, that the function is defined and differentiable throughout the interval. And secondly, that if you take h of x and substitute it for y, and if you take h prime and substitute it for y prime, that the differential equation becomes an identity. In other words, the left-hand side and the right-hand side will be equal when you substitute h in your differential equation. Differential equation solutions are typically not unique. Part of the reason is, remember, when we take a derivative, we eliminate a constant, because derivative of a constant will go to 0. And so we get a constant of integration. And unless we have some initial condition or boundary condition that defines what that constant is, then we don't have a unique solution to our differential equation. So we refer to the curve of h. If we graphed h, we call it a solution curve. And typically, if we don't have something that specifies which solution to accept, then we get a family of these curves. Open interval means that the endpoints a and b are not included as points belonging to the interval. So the most straightforward way to solve a differential equation is by direct integration. So we can consider this differential equation y prime is dy dx, and that's cosine of x. If we take this dy dx as cosine of x and we multiply both sides of the equation by dx, then we would have a perfect derivative dy on the left-hand side and the integral of cosine of x dx on the right-hand side. When we integrate that with the indefinite integral, we'll get the sine of x, and then we'll get this constant c, the constant of integration, which is an arbitrary constant. So this is the family of solution curves that I was discussing in the previous slide, where the different set of curves comes from selection of different values of c. So geometrically, the general solution of a differential equation is a family of an infinite number of solution curves, one for each value of the constant c. Now, if we choose a specific constant of integration based on some criteria, then we obtain what's called a particular solution of the differential equation. Now, unfortunately, particular solution is also used to refer to what happens when we have inhomogeneous differential equation. So I don't particularly care for the use of the term particular solution here. If I were writing this textbook, I would probably call this a specific solution. But you will see this in the Wiley textbook written in this way. So one example of a very standard differential equation that's very common in the sciences and engineering is that of exponential growth. Here we have y prime is equal to ky, where k is some constant. If k is positive, then this solution to this becomes e to the kt, if t is the independent variable, where k is a positive number. And so here we see the family of curves generated by that solution. This can apply to things like bacteria growth or population growth, anything that models a positive exponential growth. If you have small populations in a very large country, then this applies to human population growth, and it's called Malthus's law. This is a very classic human geography economics example of positive exponential growth. In reality, in a practical situation, positive exponential growth is almost always limited by some limiting factor. For example, if you have colonies of bacteria, eventually the bacteria will run out of food to feed their multiplication, and so if there's nothing for the bacteria to consume to grow on, then you no longer have exponential growth. Exponential decay is a little more common in electrical engineering. Most of you are aware that exponential decay models, for example, energy stored in an RC circuit, where the exponential decay rate is a function of the resistance and capacitance. This particular figure, it illustrates solutions for various negative values of C, or that constant if we chose to use K, as in the previous equations. So when y prime is kx or cx, and that k or c is negative, then we would get exponential decay. So the family of curves becomes a family of exponential decay curves. Now, one of the ways we select a specific solution out of the family of curves is if we have an initial value problem, sometimes also referred to as a boundary value problem. So initial value problems have an initial condition or a boundary condition that gives you some known value of x and y, and usually this is a 0. So for example, an initial condition would tell you that if you know for a particular value of x, often 0, the value of y, then that's an initial condition or a boundary condition, and that can be used to determine a value of an arbitrary constant c. So this is going to tell you which member of the family of curves forms a specific solution. If you have an ordinary differential equation plus an initial condition, it's called an initial value problem. And both the differential equation and the initial value would have to be special, would have to be specified in order for you to get a specific solution to the differential equation.